Hi, calculus students. These are notes for, we're going to call it 11.1, but I think that I'm not going to assign any problems from that section in the book. So this is, you could call basic parametrics. Parametric, there's an E in that word somewhere. There it is, right there. Basic parametrics. So you did some parametric equation stuff in pre-calculus, and we have pretty rich context for it now, especially if we allow ourselves to think about physics. Maybe just remind you first that here's an example of something that's not parametric. Some function, regular old y equals f of x. So y equals x squared, y equals sine x, y equals whatever you want things happening to x. That's not parametric, that's just a regular function. Something that is parametric is called parametric because x and y are defined in terms of a parameter which we usually call t. And it doesn't have to represent time, but it's very often the case that we think of it as a time parameter. So in physics, of course, lots of things we look at as they're changing over time, and time is often the variable that we plot on the horizontal axis. So, for example, we might have x of t and y of t. Those are our two. Here's the x-coordinate in terms of t, the y-coordinate in terms of t. And sometimes we see this pointy bracket notation that looks like that. You might run into that sometimes. And sometimes you might also see x equals and then some function of t, and then y equals some function of t. Different ways of writing those. So why would you want to have parametric equations? Well, in any kind of two-dimensional motion, if the x and y coordinates are changing independently with time, for example, in projectile motion, this is linear and this is quadratic. In uniform circular motion, these are both trig functions, but not the same trig function. And lots of situations where we might want to do this. You could have three-dimensional parametric equations also if you had a z here, although we're not going to do that. Okay, so let me give you an example, a simple one. So let's say we have the parametric equations x equals 2 minus t and y equals t squared minus 1. And we wanted to just play around with this, see what it looks like and what it feels like, that sort of thing. Well, just like in algebra class, if you come across some new y equals x, maybe the equation for a line or something, you might make a little table, an xy table. We're going to do the same thing here, get a feel for this. But the thing we're going to be picking is we're not going to be picking x values, we're going to be picking t values. So I'll put that first, and x and y. And it doesn't have to be the case that time starts at 0 or the t variable starts at 0. But if we're interpreting it as time, it would make sense that whenever we start paying attention, that's time 0, and then time moves only forward from there. So I'll pretend that that's what's happening here. And then we can find our x values. So 2 minus whatever the t value is. And then 2 minus that, and you can see what's happening here. And here, square the t value, subtract 1. And square the t value, subtract 1. So there's our little table. And if we wanted to make a graph of this, there's different graphs that we could make. If this was for projectile motion, for example, when we did the basketball shot, and that was our first look at that, we made separate graphs. We made an x versus t graph for the horizontal motion and a y versus t graph. But here I'm interested in making the x, y graph. If we did that for the basketball shot, that would be a plot of the actual trajectory of the ball. So let's see what that looks like. Let me go ahead and scale that. So here I've got the point 2, negative 1, 1, 0, 0, 3, negative 1, 8. Oops, that's not there. And negative 2, 15. So it starts here at time 0, and then time 1, time 2, time 3, time 4. So one of the features that a parametric graph, a parametric function captures that a regular y equals x function of x doesn't is this definitely has a sense of direction. And if you want to make the case that the y equals x kind of graph has a direction, it doesn't really. The calculator makes it seem like it does, and the way that we read from left to right makes it seem like they're always going from left to right, but they're not. There's no directionality to that. They're just all those points are there. Here, all these points are here, but they're definitely happening in this progression from time equals 0, time equals 1, time 2, time 3, time 4, and so on. And notice that I did not put an arrow on this end because I'm not going back to times before 0. So it also has a start here, which y equals x types of graphs do not. All right, so there's just an example of that. And pretty much, in terms of what you need to know from pre-calculus about parametric curves, that's just about it. Nothing more to say, really. So let's talk about calculus relative to these things. So how do you find the derivative, the slope, dy dx of a parametric curve? So dy dx, or in other words, the slope of a parametric curve. It's super easy. It's exactly what you would think it would be. Dy dx is equal to, well, you can't find that directly, but you know what y is in terms of t, so you find dy dt, and you put that over dx dt. That's dy dx. That's the slope of the path. Maybe I'll just put that here in parentheses. It's the slope of the path. And you should note here that it is not, all right, let's get that over, it's not a speed. This is the slope of the actual path that the thing is traveling on. The time has canceled out. This is dy dx. It's not the rate of change of something with respect to time. The time factor has sort of canceled itself out, although this will be in terms of t. This is giving us the slope of the path that it's traveling on, separate from the speed of it. All right. How do you find the second derivative? This is the concavity. And again, this is the concavity of the path. It does not have to do with time. You can see right there, there's no t in there. The concavity of the parametric curve. This is a little bit weirder. So remember that we have this operator form of the derivative where we write like d dx. This is the, I'm going to take the derivative with respect to x of whatever you write next. So we could say the second derivative is like taking the derivative with respect to x of the first derivative. Could write it like that. And you can also see, this is the motivation for why we write the 2's in the way that we do. All right, well, how are we supposed to do that? The problem with this is this expression, which we'll get by doing this, is going to be in terms of t, and this says to take the derivative with respect to x, but this is in terms of t, and this says take the derivative with respect to x, but this is in terms of t, so that's not going to work. So if this is true here, then I can rewrite my operator as this. Right? I can say here I had dy dx and I rewrote it like this. And now if I have d dx, well, I should be able to do the same thing here. And that is going to be operating on this. But notice that this is just dx dt. This is the operator. So this wants to take the derivative of that. And that's going to work because this is going to be in terms of t. So we can do that. And it will just feel like taking the derivative again. But then we have to divide by dx dt. That's the bit that seems weird. And this is why we have to do that. All right. The last thing I want to show you is when you have a parametric curve, how do you find the length of it? And you might be thinking to yourself, well, let's see, how do you find the length of a regular curve? And you might be scratching your head, thinking, I must have forgotten that. Well, you never learned it. We don't know how to do that. The reason we've put it off until now is because I think it's most intuitive to learn how to do that first with parametric curves and then go back to how to do it with regular curves. So let's say we have some parametric curve. We want to find the length of it. I wouldn't be going from x value to x value. I'd be going from time t1 to some other time t2. And if I took a little piece of it here, and I pretend that this piece is infinitesimally small, then this is like a dx, and this is like a dy. And then that means that this, the hypotenuse, right here, is just the Pythagorized square root of dx squared plus dy squared. And that'd be that length for this little tiny bit. And if I would like to find the length of the whole curve from t1 to t2, then I need to find the sum of all these infinitely many tiny little things. That's an integral from t1 to t2 of the square root. Now, I need things that are in terms of t here, so instead of just dx, I can say, well, that's like dx dt squared plus dy dt squared with respect to t. And if you think about the algebra that would happen here, this expression is precisely equal to this expression. So we are good. And that's how you find the length of a curve. Easy to do when you're in parametric mode. And once you have that, it's also easy to switch it out of parametric mode and understand why it looks like it does when you're not doing parametric stuff. The problems that, it's very common for problems of this type to be either calculator problems, where you have to find this, or evaluate this integral with your calculator, or sometimes you'll just be asked, like in numbers 11 and 12 of the assignment you're going to do, this go-round here, that you're just asked to write the expression, the integral expression, but not actually evaluate it. So there you go. Parametrics are fun.